So what we're used to is graphing things in x and y coordinates. The so-called Cartesian coordinate system, first conceived by René Descartes in the 17th century. That's where you have x and y, as distances from the various axes to help figure out where you're at. So coordinates of a point could be x and y. And that's one way to create a coordinate system. But there's a lot of other ways. In fact, I think I remember hearing Isaac Newton came up with about 10 different coordinate systems. And I can't imagine what those will all be. But at some point, probably in Calc 3, we'll start dealing with spherical coordinates. But for now, we're going to deal with polar coordinates. So a different way to try and envision where a point is not just to figure out, well, what its x and y coordinates are. An alternative to that, and I'm just going to steal a little guide here for a second. Let's see, like that. An alternative to specifying coordinates in x and y is to start by specifying a radius, that is what distance you are away from a particular fixed point. But that radius is going to have an infinite number of points at those angles, or at any angle. So in addition to specifying the radius, you're also going to specify an angle. That angle is going to be your theta. If I bring that back over to here, I'm going to get theta here and the radius here. Obviously, these are my x and y's. So we can proceed to try and make some connections here between these two types of notation. Now, I'm assuming that that's going to be a right angle. So what's one easy connection that we can get here? Andreas? So we got, is there an easy connection, easy relationship between x, y, and r? That wouldn't involve all three, but we can use cosine theta. In fact, we will do that in a minute. But I guess the basic one I was thinking of is just the Pythagorean theorem, right? X squared plus y squared equals r squared. So that's one nice relationship that you can get between these two, or between these three. Syed, you said one as well. Let's take a look at cosine of theta. What's cosine of theta going to be? There you go, x over r. Now you can rearrange that if you multiply both sides by r and get that x equals r cosine of theta. And that's a handy, nice thing to have around. Likewise, I can do the same thing with sine of theta. What does sine of theta equal? Y over r. And if I solve for y, I get y equals r sine theta. So I've got a couple nice relationships that I can use here. These three are going to be the most common, the most helpful. There is one more here, and that is the tangent of theta. What's the tangent of theta? Y over x. Good. Opposite over adjacent. Now, occasionally you might have the use for inverse tangent of x or y over x is going to equal theta. That one gets used a little bit more often than it should. But, all right, here we go. We got some nice relationships between our variables. Let's take a look at what it looks like graphing points in polar coordinates. This should be your reminder. So we got some points here. Let me label them, 1, 2, 3, 4, and 5. So these points are always in the form of r comma theta. My suggestion is that when you're working with these things, the first thing you do is you find theta, and then you move out the radial distance. So you've got a different type of graph here, but still is going to allow us to plot these points. Pi over 3, that's our 60-degree angle. So we're along this line someplace, and you want to move a distance of 4. 1, 2, 3, 4. So there's our first point. Likewise here, 4 and 5 pi over 3. I'll let you do that one. Let me take a look at this one, because this one's going to twist things up a little bit. Our angle is 3 pi over 4, which puts you in the second quadrant. But we don't have a distance of 5, we have a distance of negative 5. Do you remember what happens when you have a negative radius? Yeah, it's like adding pi to this angle. You're going to be plotting this on the other side. So instead of a distance of 5 here, I'm going to be on the opposite side of the origin over here. So that's going to be my third point. Why don't you test yourself real quick, see if you can't find those last two. Well, I guess I left you 3. Let's take a look at these. So for the second one, that's just 4 and 5 pi over 3. So 5 pi over 3, let's see. That's just going to be right here then, right? Oh wait, that's, here we go, 5 pi over 3. Right there, so that's 2. 4 would be negative pi over 4, so instead of going counterclockwise, you're going to go clockwise. So negative pi over 4 is going to be here, but then we've got a negative 5 taking you to the other side over to here, so that should be the fourth one. And the last one, negative 4 and negative pi. Well, positive pi and negative pi take you to the same place, but that negative means you're going to switch sides over to here, so that would be your fifth point. There's a lot of cool things you can do with coordinates, polar coordinates, that you just can't do with regular coordinates. One of the interesting things about polar coordinates is that these coordinates are no longer unique. Now in the XY Cartesian coordinate system, when you have a point 4 and 2, that's it. There's no other names for it. But there are other names for some of these points. For instance, this first one I could say is 4 and pi over 3. But I can equally say that this is 4 and 7 pi over 3, which means you go pi over 3 and then you go 2 pi over 3, or 6 pi over 3. That would bring you back to this angle right here. So there's different names for these points, even though they're the same point. And that's kind of the gist of this one here. Determine where you plot each of these. A, B, C, or D. So again, just kind of giving you some choices. See if you can't figure out a few of those real quick. let's take a peek at this one, see how we're doing. We'll start out with -4 and pi over 6. Pi over 6 is here, but because we've got a -4, where am I going to end up? What point? C. 4 and 5 pi over 6, that one's pretty easy because you're just going to go to the angle and find that point, so that's going to be a B. How about the third one? What point are we at now? Yep, back to C again. Fourth one, let's take a look here. You're going to go -pi over 6, and then a distance of 4 would put you at D, but we got a distance of -4. So instead of being at D, we're at B. 5 pi over 6 is going to put us at B. Then, let's see, we've got a -4, so instead of at B, we're at D. 4 pi over 6 and 11, or excuse me, 4 and 11 pi over 6. So 11 pi over 6 puts us at this angle here someplace, and the distance of 4 puts us at D again. How about 4 and -11 pi over 6? Where's that one going to put us? A. Thank you. And finally, -4 and 7 pi over 6. 7 pi over 6 is D. -4 is going to put us back at A. So, yay. Not so bad. Not so bad. All right. So this is just kind of a quick little reminder of going back and forth between Cartesian coordinate systems and rectangular. Well, not really going back and forth, but graphing in those systems. Let's move on to example C here. We've got the point 6, -6, and we want to find polar coordinates of that in two cases. One, the first case where the radius is positive and our angle is between 0 and 2 pi. The second, where the radius is negative, and again the angle is between 0 and 2 pi. So there's a lot of different names for these types of things. But let's draw our point first. So this is example C. And I think this one will work. So our point has coordinates of 6 and -6. What quadrant is that going to be in? That's going to be in the 4th quadrant. So let's just give myself points here and here. So that's going to be 6. That's going to be -6. Here's our point. There's two things we need to determine. One of them, the first one we need to determine is this angle here. What is that angle for theta? And then the second thing we need to determine is r, so the radius. And that should be -6. Now, I don't know. Can you eyeball this and tell what the angle has to be? You can tell me in degrees first if you want. What's this little piece right here in degrees? 45, right? Because these two sides have the same length. And if those two sides have the same length, then this angle is bisecting the 4th quadrant. That's a 45-degree angle. That's a 45-degree angle with the y-axis. So if this is 45 degrees, the other way is 360 minus 45 degrees, or 315 degrees. So theta equals 315 degrees. That'd be an okay answer if this was a trig class. But because we're working in calculus, we've got to convert that to radians. Now, if you're more comfortable working in degrees, that's fine, but eventually you've got to convert that to radians. So let me remind you, 315 degrees times pi over 180 degrees. And guess what? Units of degrees will cancel. 45 goes in here 4 times, and it goes in here 5 times. Let's see, no. No, that's right. It goes in here 7 times. So I'll end up with 7 pi over 4 for my angle. Well, there's one other thing I need. I need to know the radius. How am I going to calculate how far this is from the origin? Yeah, thank you, James. Pythagorean theorem. So it's going to be the square root of 6 squared plus negative 6 squared. That's going to be the square root of 72, which is 6 square roots of 2. Nice. Overall, when you present your angles, you're going to present them in terms of r and theta. So for part A, our answer is going to be 6 square roots of 2 and 7 pi over 4. Nice. There's a part B here, but let me make sure you're comfortable with part A. Part A is kind of review stuff. Yeah, okay, all right. Let's take a look at part B. Part B, we had a different little spin on this. We wanted to have a negative radius. So for our answer for part B, we're going to start out with negative 6 square roots of 2. And now we need to figure out the angle that is going to make this the same point as what we have up here. So if we're going to have a negative radius, then our angle has to take us up over to here, right, in the second quadrant. So if it takes us up in the second quadrant, what angle would that be? 135, good. And 135 in radians would be 3 pi over 4. So again, 135 degrees times pi over 180. Now, if you're feeling like that's just really demanding, it's a lot of work there, Jeff, then no biggie. Your calculator can come to your rescue. Let's just leave off the units of pi for the moment. And I don't know why this program just takes like forever to open up, but it does. There we go. So I'll just do the 135 divided by 180. In fact, I'm not even going to get a decimal first. I'm just going to start by hitting the math key and go answer the fraction. It should give me that fraction in lowest terms. Great, there it is. So 3/4. Overall, my answer is going to be 3/4 pi. And we're done. Nice, nice. Let's move on to example D here. Let's see, is there something I want to graph? Thank you. Yeah, let's move on to example D. Find the Cartesian coordinate system for the curve and identify it. R squared equals 5. Okay. So if R squared equals 5, do we have something that we know of about R squared? R squared is really equivalent to x squared plus y squared. So I can make a nice little replacement there. X squared plus y squared equals 5. Does anyone recognize that curve? Yeah, it's a circle. What else can you tell me about this circle? I could write it as x minus 0 squared plus y minus 0 squared equals square root of 5 squared. That's kind of maybe a little bit overkill, but it might get the point across as well. There's two things that I'd want to know about this. What's the center? What's the radius? Alicia, what do you got? Center and radius? So center and radius would be the value of x that makes these square terms 0 and the value of y that makes the square term 0. So in our case, 0, 0. And the radius is always going to be the square root of the right-hand side. So I wrote that as square root of 5 squared. But if you just take the square root of that, square root of the radius, or square root of the 5 gives you the radius. Now, one nice thing about Desmos, amongst many things, is that you can graph things in Cartesian coordinates or polar coordinates. So let me just pull up a new Desmos graph here for us. So I'll just type in r equals 5. Now this isn't quite our equation, but that's a circle of radius 5. We've got something a little smaller. We've got r squared equals 5. And I don't think it's liking that one. All right, it's not. So I'd have to have r equals the square root of 5. And that's going to give us our circle of a smaller radius. You can make this graph actually look a little nicer if you wanted to hit the toolbar here and come down and switch to radians. So pretty nice. You can do some graphs with your calculator. We'll do that in a little bit. Let's work on finding the Cartesian coordinate systems for this curve and then identifying it. And I guess maybe what I can add here for us in general for example D is x minus h squared plus y minus k squared equals r squared. That's the general equation of a circle. And let's note a couple things about that circle. The radius is going to be the square root of that. So radius is going to equal r. What about the center? So we're going back to my comments to Alicia. The center is the values that make these squared terms equal to 0. So what makes the first term equal to 0? H. How about the second term? K. So h and k, those would be your coordinates of the center. And example E is not looking terribly user-friendly at the moment. So let's take a look here. Example E. We've got r equals 9 times cosine of theta. Now, if you looked at it and said, well, r is the square root of x squared plus y squared, but I can't do anything with the 9. And then you start getting really creative. 9 times, well, theta is the tangent inverse of x over y. And boy, you're getting really deep into the weeds here. This is just not the way to go with this one. Like I said earlier, a lot of people use this relationship too much. All right, that theta is the inverse tangent of y over x. I guess I get that upside down. No worries. We're not going to go there anyways. Instead, here's the trick that you want to take note of. In order to get rid of this, I really need an r there. So let's go back to this. R equals 9 cosine of theta. If I multiply both sides of this equation by r, that might bring me the success that I'm looking for. So it'll be r times this, r times this. The left-hand side is now r squared. The right-hand side is 9r cosine of theta. And I claim that's a little bit better. So how is that better? Well, I can solve for x and y is a little bit easier now. What can I replace r squared with?
X squared plus y squared.
X squared plus y squared. And on the right-hand side, this is really 9x. So, yay, that's nice. Now, we're not quite done yet. The problem's going to ask you to try and identify what figure this is. You can kind of look at this and say, yeah, it's starting to look like a circle, but what's the radius and where's the center? Well, that's a little harder to come up with. So I'll move the x squared to the 9x to the left-hand side. That's x squared minus 9x plus y squared equals 0. And now I'm going to play a game called Complete the Square.
Is that minus squared?
So what I want to do is I want to figure out what number in here makes that a perfect square. That is, I can say, oh, well, that's, x minus this squared. Now, the trick in completing the square, when you have something like this, is to take half of that middle number. Half of negative 9 is negative 9 over 2. Okay. Then what? Then you need to square that number. So I'm going to take that negative 9 over 2 and square it, and I get 81 over 4. So that's the number that I need right here. So I'm going to put that number there. Now I can't just put a number here when I'm dealing with an equation. What do I really have to do? If I add something to one side of the equation, what else do I have to do? Add to the other side. So I'm going to add 81 over 4 to both sides of the equation. So kind of an in-between step here. I'm going to have x squared minus 9x plus 81 over 4 plus y squared equals 81 over 4. So I'm going to put that in. 81 over 4, 81 over 4. The nice thing is that this is a perfect square. Might not look as nice and neat as you like, but it is a perfect square. And there's something nice about the way we did this. This number that I got here in the process of completing the square is going to be right here. I'll have a minus 9 over 2. And then, of course, I'll still have my x. So it's going to be x minus 9 over 2 squared plus y squared equals 81 over 4. Whew. So a little bit of extra work there for us at the end. Let's take a look at our center and radius. Why don't you take a look at the center and radius for a moment, see what you can come up with. Kaiser, what do you get for the center? 9/2 at 0, good. And the radius? Yeah, 9/2. Just a square root of the right-hand side. Beautiful. That's what they're looking for. At least WebAssign will be looking for. This is going to be a circle. Circle with radius 9/2, centered at 9/2 and 0. Let's see if we can get that off of Desmos here. Actually, maybe we should take a look at it not only on Desmos but on our graphing calculators. Let me do it on Desmos first so we can get a good look at it. I'll get rid of these two. And we'll type in r equals 9 cosine theta. Now, if you want to get the theta, there's a couple ways you can get that. But one of them would be just typing in theta. So there you go. Let's take a look here and see if that kind of matches what we expect. Let me plot the point 4.5 comma 0. Let's try that again. 4.5 comma 0. Yeah, that looks like it's about right in there in the middle. That's our center. Radius is that same distance from here to 0, 0. So looking pretty good. What's that look like on a graphing calculator, which is more like the tech that you're going to have on an exam? Well, you're going to get your money's worth out of your graphing calculator this semester. We're going to change our mode again. So go up to the mode key. This time, instead of parametric, we're going to go down to polar. So cursor over to polar, press the enter key. You should be flashing on polar. And then we're going to graph this. So we're going to graph this by hitting the y equals key. What's the big difference that you notice here when you hit the y equals key? Yeah, you got r equals something as opposed to y equals something. So expecting r as a function of theta. And with fear and trepidation in your heart, you type in 9 cosine, and you're like, where's the theta? Well, your x key. Now that you're in polar mode, your x key gives you your theta. So there's our 9 cosine theta. Let's set up our window. Our window's going to have some more adjustments, just like it did with parametric mode. Now it's asking you, what should I let theta equal? Can anyone tell me what theta max is? Yeah, it's 2 pi. Thank you, James. So 2 pi. Theta step. Right now I got it at 0.05. You can do 0.1 if you wanted to. Then you're going to have to set up your x-min, x-max, y-min, y-max as before. I think, just like our parametric mode, that once you have theta figured out, you can let your graphing calculator figure out the rest. What would you have to do to let your graphing calculator figure out the rest? Where to set it up? Zoom 0. Nice. There's your graph. One kind of complaint though. What's this figure supposed to look like? Circle. And I know it's football season, but I don't think I'm really stretching it too much to say that it looks kind of like a football. All right. So if that bothers you, if you're like worried, it's like, oh boy, that doesn't really look like a circle. There's one more adjustment you can make to your calculator. Hit zoom 5. That's zoom square. It squares things up in terms of your perspective so that circles look like circles. So now you look at that and go, okay, that's what I expected. A couple other thoughts on your settings here. If I set theta step to be something big like 1, what it's going to do is it's going to start out and plot theta equals 0 and then theta equal 1 all the way up to 6, and it's not going to have enough points to actually look like a circle anymore. Kind of looks like a mess. So there's a little trade-off. I mean, if I choose theta step too small, like 0.001 or something like that, now it's going to take forever. Well, not too bad, but it takes longer to graph this. So, choose a happy medium, whatever works for you. Pay attention to your problem. Sometimes it goes between theta 0 and pi or 2 pi. It can change. All right, looking good on that one. Let's do a couple things in the opposite direction, that is starting out with, well, I guess it's still the same direction. Start out with polar and work towards rectangular. So a line through the origin makes an angle of pi over 6 with a positive x-axis. So your equation is this. But what would the equation be in Cartesian coordinate system? Well, and I guess maybe I'll break down and add it to us here. Although, generally speaking, you're not going to use this relationship that much. Theta equals the tangent inverse of y over x. Just solving for theta from this relationship. So, looking back here, I can replace that theta with the inverse tangent of y over x. So tangent inverse, or the arctan, of y over x equals pi over 6. That still looks pretty messy. Doesn't look like it got us very far. So, what else could I do? Well, I can take the tangent on both sides. Let's try that. Tangent inverse of y over x equals tangent, no, actually, well, that's okay. I want to take the tangent on both sides. Tangent. So I'm going to take the tangent of the tangent inverse of y over x, and that's going to equal the tangent inverse of pi over 6. I meant to write that in the same color, my bad. Let's take a look at the left-hand side first. What's the tangent of the tangent inverse of y over x? What happens with those two functions when they collide? Yeah, it's like your particle and your antiparticle. When they collide, they annihilate each other. All you're left with is y over x equals, here's a good question for you. What's the exact value of tangent of pi over 6? If you're looking at that and like, yeah, I got nothing. Yes, square root of 3. But if you're looking at that going, yeah, I don't really know what that is, here's a little trick that you can try. Take the tangent of pi divided by 6. Now you're going to get some ugly number here, which you might not recognize, but then hit the square key. And now that number should look a little bit more familiar. Does anyone recognize 0.33333 as a decimal? If you don't, hit the math key. Oh, that's 1/3. Now remember, we squared to get that. So really, what this is on the right-hand side is the square root of 1/3, or better yet, 1 over the square root of 3. If I wanted to solve, I could multiply both sides by x and get y equals 1 over the square root of 3x. If you're bothered by that square root in the denominator, don't worry, I'm not bothered by it there. Rationalizing denominators work for a different course, not for this course. Okay, how are we looking with that one? Last but not least, we want a vertical line through this point. We can come up with that equation. We'll also take a look at it in polar coordinates as well. So if we've got a vertical line through the point 4, 4, let me kind of just sketch in a little graph here real quick. We've got a vertical line through this point. What's the equation of that vertical line going to be? X equals 4. Great. Now you could, if you want to, do that in polar coordinates. So to go to polar coordinates, what is x equal to in polar coordinates? Well, you can look back at the start of this. X is r cosine theta. So we get r cosine theta equals 4. Now, your calculator and web, not so much Desmos, your calculator is going to typically ask you to solve for r. So you could rewrite this as r equals 4 over cosine of theta. That should give you a vertical line at x equals 4. Let's test that it does. In fact, let's test it on our graphing calculator. Since we've got a nice graph up here anyways, let's see if we can't skewer that thing with a vertical line. So I'm going to graph them both just for giggles. 4 divided by cosine of theta. And bam, there you go. There's your vertical line. Pretty nice. One of the cool things about Cartesian coordinate or polar coordinates is that some of the graphs you can draw are really kind of nice. And let me think about one of them right off the top of my head. It's called a cardioid. And I think we've got one lined up for us in the form of example G. R equals 1 minus cosine of theta. And let's shut these off. Can anyone suggest the reason why they call that a cardioid? Yeah, it looks like a heart. So the only thing that bothers me about that one is that it's kind of facing to the left. Let's see if we can't get it faced upside, face the right way. This would be 1 minus sine of theta, I think should work. There you go. There's your heart. Yay. It's about as romantic as mathematics ever gets. So lap it up now. Yeah. If you're counting on math for your romance, actually there is a book about, I think it might be called The Mathematics of Sex or Mathematics of Romance, but one of the two. But it actually brings a lot of mathematics to bear on the process of dating. It's pretty amusing, really. In any case, are we okay with this graph? There's other graphs too. If this number in front of your sine or cosine is bigger than this one, then you're going to get what's called an inner loop. So let me put an A here and put a little slider for A. And when I adjust that slider, you can see an inner loop start to form. If that number is between 1 and 0, then you don't get that dimple at all. Well, you get a little bit of a dimple, but you don't get that inner loop. It's once you pass 1 that you're going to get that inner loop. So, pretty cool. I believe this is called a limacon with an inner loop. And something like this would be called a limacon without an inner loop. Nice. How are we looking on polar coordinates? Let's get a little refresher maybe. All right. Are you comfortable graphing? Why don't you try and graph one of our cardioids here. Try and graph r equals 4 minus 4 sine theta. And then I'll graph a couple other ones here that are kind of interesting. R equals sine of 3 theta, sine of 4 theta, sine of 2 theta. Now, if you want to, if you're looking at this and it's like, you know, I'm going to need this equation later, you can shut off that equation, at least in terms of its graph, by pressing the Enter key with the cursor on that. It'll change the look of the equal sign. It won't have that dark emboldened look anymore. It won't be white on black. And let's just put in 4 minus 4 sine of theta. Now I'm probably going to want to adjust the window again so that I can see this graph in its entirety. Because if I graph it right now, I'm thinking that it won't fit too well. Yeah, you're getting some of it, but not all of it. So as a reminder, zoom 0. That should do things pretty nice. We can probably follow that up a little bit with one last little thing here, and that is to square off the axes. I mean, this is pretty nice. It gives you a good shape there. And that's really all we really need. But if you had zoom 5, then it's going to trim it up a little bit. There you go. And that's another look at this. Let's finish up with a couple of these things. Let's take a look at sine of 2 theta, sine of 4 theta, sine of 8 theta, etc. So let me get rid of those. So r equals, let's say, 2 sine of 2 theta. And that's kind of neat. 2 sine of 2 theta. We get a 4-leaf clover. So a 2 there gives me a 4. 4 gives me 8. What do you think a 6 is going to give me? How many leaves do I have now? 12. But here's a twist. I can go up to 8. Now I get 16. But what if I did 3? Uh-oh. What if I did 5? Oh, I get exactly 5. 7. And it's going to be the same way for cosine. If I put in a cosine here, cosine of 7 theta, I don't need that extra s there. There we go. So what's the general pattern here in terms of predicting how many leaves? If I put a 3 here, how many leaves will I have? 3. If I put a 4, how many leaves will I have? 8. And then 5, etc. To understand why this happens, it's really, in this case, very helpful to have a graphing calculator. So let me put in those equations. Let me put in, say, for instance, 2 sine of 2 theta. And then I'll hit zoom 0. Let my calculator figure out where I want to graph this thing. And I should see something that has 4 petals. And you see it nicely traced out, etc. Great, it's got 4 petals. But what if I put in a 3 there? So let's go back here, and I'm going to put in a 3. And I want you to watch this very closely. I'm going to slow it down just a little bit by increasing theta step. Let's see, oh, it's already 0.001, so that's pretty small. If you did 0.001 on your calculators, I think it might take a little bit. 0, 0, 5. All right, so I'm trying to make it even slower. Zoom 0. See if you can't figure out why we're only going to get 3 leaves here as opposed to 6. What's happening? There's our 3 leaves. You can't really see it. Let me adjust one thing here. There's a little setting that you can play with in the style. So I'm going to put a little cursor on this. If you go over here to the left, then the style that you can set up, that first one, let me click OK. That first one's going to show you exactly where you're plotting things. So when I go back and graph it, now you can see where it's plotting. And you're going to get the 3 leaves as before, but you should see something else that it'll explain a little bit about why we're only getting 3 leaves and not 6 leaves. So here's the end of our 3rd leaf, but then watch what happens. Because you're varying theta from 0 to 2 pi, it just happens that it's going to trace out the same pattern, one more time. Whereas when theta has an even coefficient, you don't get that double tracing of this. I could have got this same graph if my window settings went from 0 to pi as opposed to 0 to 2 pi. But if I did that with an even value in there, well, then it would only give me half of the leaves that I expected. Okay, any other comments or thoughts on polar, or your refresher on polar? All right, let's shut it off here.